Today we're going to see this example that we have in front of us is a two mechatronic system is an accelerometer with its measuring circuit, because the what we have in here on the left hand side is a device that where the accelerometer is attached. It has a housing, and the way it works is you have this mass inside that can move, and it has a spring and a damper attached to the housing. And when this body experiences an acceleration, obviously by Newton's first law, as you know, the law of inertia, this mass is not going to want to move, and in doing so, by the input and this not wanting to move, compresses this material, which is a piezoelectric crystal, and in doing so, the piezoelectric crystal produces a voltage that we need to measure. So I'm going to put some questions, and then we're going to address those answers one by one. First of all, how does this operational amplifier work? Is it really a transformer? Is it a source? What is it? How should we put together the mechanical part, the piezoelectric part, and the electrical part together? Question number 3, what transfer function should we look at? 4, can we use the information from the root locus of that transfer function and the frequency response of the transfer function called body plots to give us some important information? And so let's take those questions one by one. So I'll disappear from here, and here's the situation. This is the mechanical side, this is a piezoelectric transformation, and here's the electrical side. What is important here is that I think it's obvious that we have a simple mechanical system here, but what is not so obvious is how we get the signal from here so we can measure what the acceleration is. Well, we understand from what I told you the piezoelectric idea of this, this material, and the way this goes, this is this operational amplifier and this little circuit is used to amplify the signal and to measure the acceleration by establishing a relationship between the voltage here and the input. So you could see in here we have a mechatronic system in the sense that the transfer function that we will be analyzing is a voltage output, while the input is a mechanical motion, right? Is an acceleration. So obviously there has to be here some transformation of units and everything, but on the electrical side, the way this works is this device, this operational amplifier, is not a passive device. This thing is externally powered. That's what we need to understand. And the purpose is in here that the current, the input current here is 0. You know that elements in systems communicate with each other with two variables, right? With an effort and a flow. That means a current and a voltage in this case. But the idea is to suppress the current and let only the voltage, so that this operational amplifier could act as the name says, as an amplifier, so that the voltage would be big enough so we can actually measure. That's the purpose. What most students have difficulties understanding this idea that we suppress the signal here, and yet this is this still transforms. Well, the statement I just made is totally contradictory with the idea of power conservation, right? So this thing is not a transformer in the sense, because transformers are power conserving elements. This guy is not. So it's some sort of a hybrid, you may say, is a different guy. So in this case, we have chosen to represent it just as a control source, that would amplify the signal. That's one way. Another option would be to do the transformer, and then in the MATLAB file suppress the current. That will work too. However, it will not work on the graphics. So in the graphics, you're gonna have some challenges in there. So the best way and the easiest way that I found out to solve this problem is to represent it as a control source. Yeah. So that's why you have it as a source of effort, but it has to be only source of voltage. See, that's why that thing has no current. Okay. So in this case, and in fact that's what a source is. A source of voltage would have a very minute current, right, which is appropriate for this. So what is left at this point for me to do is to begin putting together the entire system, and then let's experiment with the different possibilities of our operational amplifier and the different difficulties that we can have with it. So I gave you on that write-up the model of the mechanical part, which I am going to do first, and we could do this this model of this system, and then I think I had it all, right here I had it all nice and simplified. So let's enter this first, and then we'll do the piezoelectric transformation and then the circuit. Okay, so let me just move it a little down here this way, and then I am going to enter this into the CAMG software. Okay, I think we have one running in the background right here, so that we can enter this into the CAMG. So I'm just going to put it to the left in there, so that we have it in here. Okay, then we might need to move this to the right a little. I mean, those are the things that, for purposes of seeing this really well. So now we're here. Okay, let's see. Okay, so in here you have a source of effort. I mean, the way it is in here, we couldn't perhaps the source of effort, you could even put it on the under, so that it would look like it comes from under the ground. So, and then you put the 1 in here like this, and then you have the I element in there. This is right here, and then we have a C and the R elements in here. I guess the C is first. It really doesn't matter the order in which we do this. And then you have the R element in here like this. You see, so this is this. I just chose to put the source on the bottom, that's all, because I want to build the piezoelectric transformation to the right, So I made myself, I left it free on this side. That's all I was doing. So in here, we're gonna go and we say, okay, this is my. So we'll come back again in here to this write up, and we have the piezoelectric transformation, right? That piezoelectric transformation is in here, see? So this one we should be able to attach directly over here. I'm just gonna go back again here, and we go to the TF element in here, which is right here, and then we say, okay, do this please. And on the other side we are going to have another one in here, which is like this. Yeah, this would be the piezoelectric transformation as I see it right now. But let's see what we do to connect to the electrical system. And the electrical system is represented over here like that, see? And actually on this side we are using a 0 to connect, because in this case you see what you're saying here, from the picture, this one, yeah, you're saying this is a 0, right? Because here comes this current, here comes this other one, but this one is 0. So it is a 0 junction. That's why we need to represent it like this. So I had it a little bit simplified. Yeah, right there. Okay. So what we're going to do is, instead of the 1, directly we connect it to the 0, and we implement this bond graph model that is on the left hand side into the CAMG software. And that is, so I'm hopefully that I am back in here. I am going to we need to move this up a little bit because I don't see the delete button. So yeah, there you go. Now I can see it. So in here we go. Yeah, let's try to see if we can get it back to life. Hopefully we didn't affect the system in here in such a way, because right now we are not seeing the mouse. Okay.
That's what happens whenever you use that program. If you click in the window, you can't move out of it.
There we go. We're finding here. So we have in here delete, and then we're gonna put this directly to the 0 junction here, like this, and then we have to build the other one in here, which is this one right here, and this is 7 according to this drawing that I have in there. I'm gonna try to use the other one in here. We have a, because we need the I think we have a 0 on the right hand side, right? Right here. Am I correct?
Yes.
Yeah, okay. Here we go. And then I'm trying to put the same numbers. And then if you put this SE over here, and you do this is what you probably did. You clicked on this like that, and then you didn't think anything of doing that, and then you did this. So you keep on doing, and then you see this, all of a sudden this thing has something funny. But I'm going to tackle that explanation when we after we complete the whole thing, because that's part of the question, you see. So in here you have the C element in here, and then you have an R element over here. Yeah, you know that everything that is red in CAMG is a warning that something is funny. Well, two things are funny here. You know, this C element and this SE. So if you don't give it much thought to this, you are gonna get stuck here. But what we need to do, remember, what he was saying is a signal. If it is a signal, it's not a true bond. Why? Because this F9, which would be the current, is 0. So this bond in reality does not exist. You know, this thing is like this. And you see what I mean? It's got the C element. But CAMG has the ability to put this one in here like this, that it won't affect anything, and the whole system will work fine. Because this symbol that you have with a half arrow in the middle, it means it's not a true bond, but rather only one of the signals has a value and the other one does is. So the moment that we put an AC in there, you are saying only the voltage counts. That's the message here. Because like I told you, we could have done it this, and this one thing to talk and another one to actually see it. Let's say, let me show you what I was trying to say. If I do this and I say, you know, really this thing looks to me that this is a transformer. So I just go over here and I said, this is a TF really. Okay, so let's put it in here, and then I connect it here, and I connect it. Wow, that even caused other problems. But I go over here. Do you see what I mean? Why is all red in there? The reason is the very same problem. This guy thinks that it has the value in there of both signals. That's not the case. So in this, the conclusion that I'm trying to help you reach is that the operational amplifier is not a transformer, is not a power conserving transformer. It is a transformer in the sense only to change the voltage signal, but not the current. Okay, that's why we represent it with an SE. So we need to go back to what we had. This is the problem. This 9. See, everything else works fine, and the reason that now the TF is red is because TFs in CAMG are power conserving elements. So we cannot do it this way. So for that reason, we have chosen to represent this as a control source. And so we put an AC over here like this, and then obviously the bond in there. This is good enough. If you if you like, you can do this, so that is exactly as my bond model there on the left hand side, and you do this. This is fine. Okay, it's perfectly fine. So once you go to MATLAB, Then what are we going to do? Then we need the transfer function between E12 and E1. We need a relationship between the output voltage and the input acceleration. That's the idea. Okay, so what we need to do at this point is to go to MATLAB and do that. Okay, so let's just go here to the interface, and then we're gonna go to MATLAB. Okay. Okay, so we have right now the bond graph model on the screen, and we have also the files that were produced from CAMG. The question is now, how do we relate this voltage on this capacitor to this input acceleration? The concept is pretty simple. The output that we are looking at is E sub 12, and the input is E1. So in order to do this, we need to specify the output. We come to the MATLAB files that we found. Make sure that you're on the CAMG SYM file, and then we need to go to the binoculars in here, and we say, would you please find me where E12 is, and click on return. Computer didn't find there. Okay, hold on, let's see, where are we here? Maybe it's gotta find E12 in here. So now we have produced the files in here. We are about to find out, we were trying to find out what E12 was, and so we have found where it is. What we need to do is to tell the computer that this is my output by suppressing this and activating this CAMG SYM file. Excuse me, that's where we are right now. CAMG SYM file. Okay, so in here we go output number 1. So we tell this is the 1, and this is 1 in here, and this is 1 in here, and we need to just in here the new version doesn't like the statement simple, so we're gonna do without it. New version of MATLAB, I mean. So now we're ready to run. So if we run this, the objective is to find the transfer function between E sub 12 and the input input in. And so here we go, there's the matrices, and these are the transfer function matrix that we have. It has two we have established the transfer function matrix right here. It has one for the first input and one for the second input, but you see the first input, you have to see it in here, is SE1. So, and the second one is this. So the one that we really care is this one right here. Yeah, right here is this, and this is the denominator right here. If we give the values, then we could obtain the body plots as well. but those are the values that we need to enter for all the physical parameters that we have, and that's what you need to do in your assignment, because you are gonna come in here and put the values in this, where the parameters right there, these ones. And we could see what will happen if we set everything to 1 just for the, just seeing the mechanics of it, not that it has any significance to the problem here, but just so that you can see it, because you need to enter the values that I give you. So so we go in here, we go in here, let's say, let's just, so that you can see what will happen. This not, like I say, I repeat, these are not intended to be values that relate to this particular example, but just to the mechanism of executing and obtaining the transfer functions and everything here. So these are numerical values now. There's the transfer function, like you see in here. We care about this one, and the computer, as you go in here, automatically has gone and say, okay, we want the body plots, the root locus plots for both transfer functions. These are the ones for yours. This would not be. And then we have also done the step and impulse response for both of them. So that's to show you how we would be able to obtain the output of the voltage in relationship to the input. So